I thought what I'd do is just sort of maybe summarize some of the key concepts from the chapters, answer any questions as we go along. I also have copies of old exams we can go through if you want to go through some of the problems in the old exams. And hopefully I can get all of this recorded on my computer so I can put it up for people to watch. I know there's not much time before tonight and tomorrow afternoon, but I've had a lot of requests for that. So we'll see how well I can draw on this on a big white screen. So, Chapter 1. Let's start with Chapter 1. What are the key things that were covered in Chapter 1 in terms of topics? Let's see. Chapter 1. Okay, we were talked a lot about bonding and how to represent structures. So if you recall, we talked about the differences between ionic and covalent bonds, right? Ionic bonds are bonds in which you have electrostatic attractions between atoms because they are ionized. So we have plus charges and minus charges, and it's electrostatic attraction. Covalent bonds, what's the difference between that and a covalent bond? Covalent bonds are sharing of electrons between the atoms, and those are stronger bonds actually. It holds those atoms together because the nuclei can't get very far apart if they're sharing the electrons between them. Whereas ions, if you have solvent around and you can stabilize them, can separate in solvent. Okay? Hopefully that's not a concept which people have difficulty with, and to be honest, other than recognizing that as we talk about other kinds of chemistry, there's nothing really to ask on the exam about whether, I could always ask if this is a covalent bond, but I think you all know that by now, so you've had enough chemistry to know that. What is important is to recognize properties of molecules like electronegativity, so that's another one. Remember, if you look at the periodic table, as you go to the right and up on the periodic table, the atoms become more electronegative. That is, they pull the electrons closer to them. They're more, the nuclei are more positively charged. They hold on tighter to those electrons. That goes into some of the concepts we were talking about in class about polarization, right? Like we're talking about in Chapter 4. You will need to understand the concept of formal charges. So when we have more or less bonds to an atom than its valency requires to be neutral, then it must have a formal plus or minus charge, depending on the particular atom and the number of bonds and the number of lone pairs. So we'll talk a little bit about that. How to represent structures. So important to know valence electrons for atoms and how they would be represented in a Lewis structure. Because oftentimes, this is really important, because oftentimes we don't write them when we draw structures. When we're drawing Kekulé structures or line structures, we don't write the lone pairs oftentimes. You have to assume and know that they're present. You know that there's a lone pair on nitrogen or that there are two lone pairs on oxygen. Okay? If there's no formal charge and there's two bonds to oxygen, you know there has to be two lone pairs in order to make the octet. A concept that a lot of people have trouble with is resonance, and we can show some examples of that. Resonance forms. Geometry of molecules. I think in Chapter 1 it was just talking about electron repulsions in the VS-EPR model. I think the important thing I want you to get about VS-EPR pictures of molecules is just understanding that things aren't flat, they adopt 3 dimensions, and they do that because they want to adopt the lowest energy state possible. Okay? So if you have 4 bonds to a molecule or to an atom, the electrons in those bonds want to be as far apart as possible, and that describes a tetrahedron. We talked about representing reactions, so for example, using curved arrows to represent electrons flowing, and as we move on in the class, we'll be using this a lot more when we're actually talking about different reactions. And finally, Chapter 1 includes some discussions of acids and bases, and Lewis acid and bases. Okay? And within that, of course, is things like how to think about the structures of molecules, changing the strength of the acid, and what things are important for the strength of acids. The pKa, how that affects equilibrium in acid-base reactions. And so if you look at all these are ugly drawing, but my writing's terrible on here. But if you look at all these topics, which ones do you think you're having the most trouble with or want to spend the most time on reviewing? Or I guess I should say, are there any that you think we don't need to review? Bonding you want to review?
No, we don't.
You don't need to review bonding? Oh, ionic and covalent bonds, yeah. I agree. If you don't know that by now, I think you would need to go back to general chemistry at this point. Electronegativity, I don't think anyone really has difficulty knowing what's more electronegative or less electronegative, right? I think it will be useful to show some examples of formal charges, maybe some Lewis structures. Resonance, definitely. Okay. And then maybe a little bit about acid-base strength and equilibrium. I think that's probably what we should focus most on. So, formal charge. How do we calculate formal charges for molecules and atoms in the molecule? Formal charge. Okay. Basically, it's you have to account for an atom, the number of bonds, the number of unbonded electrons to it, and does that match what its original valency is, the number of valence electrons that atom would be in the neutral state, right? And if it doesn't match, then you have either a plus charge because it has more bonds and something else is, quote, owning those electrons, or it has fewer bonds, or there's extra lone pairs. So formal charge, right? Remember the simple formula? Number of valence electrons, right? Oh boy, I'm going to forget this. Minus the number of bonds. Okay, that's shared bonds, covalent bonds. That could be sigma bonds or pi bonds. Minus the number of bonds, minus the number of lone pairs, or unpaired electrons. Okay, so for example, if you just take something like water, okay, oxygen, if we calculate the formal charge for this, it should come out to be 0, right? And that should be number of lone pair electrons, not just the lone pairs. So oxygen has 6 valence electrons minus 2 covalent bonds minus 4 non-bonding electrons in lone pairs, and that equals 0, which is exactly what we should have if we have an oxygen bonded with 2 bonds, right? And if I didn't draw the little dots for the lone pairs and I have it neutral, you should know that there's 2 lone pairs on there. All right? What about something like this? And I want to focus on the carbon in the middle. What's the formal charge for the carbon in the middle? Okay. Valence electrons for carbon, 4, minus how many covalent bonds? 3. Okay. Non-bonding electrons on there? No, there are no electrons on carbon. I didn't draw 2 electrons. So that equals plus 1. So if you have a carbon that is missing a bond, it has a formal plus charge. And we represent that by writing a plus charge by it. That is an example of a carbocation. We're going to talk a lot about that in Chapter 4, by the way. Carbocation. Okay. So if I think about, well, let me just do this. Let me draw this molecule. Okay. And this, and I want to tie this in with resonance forms. I can draw resonance structures for this molecule. But there are going to be some charges. So if I think about how that lone pair being next to the double bond in the ring could potentially move like that, or I can envision it moving like that, right? I can draw a resonance form where now those electrons were put up on the carbon there. There's a double bond to the nitrogen. Okay. And now we have a structure where atoms don't have the right number of bonds, right? Or things like that. So let's take a look at this. And I should point out one thing that I didn't write here is that there's a hydrogen on this carbon. I'll just draw it here. Okay, so you should be able to recognize, if I draw that resonance form, that represented that way, there are atoms which have charges on them, formal charges. Okay? So how many can see right away that there are two different charges in the molecule? Can you see that? Well, let's look at it. The nitrogen, for example, now has 4 bonds to it, so it's not its usual 3 bonds, so there must be something different there. Nitrogen has 5 valence electrons, minus 4 bonds, minus 0 non-bonding electrons, because we use that to make that second bond. So that has a +1 formal charge. So nitrogen has a plus charge. Okay. The carbon here has also been changed. It has a lone pair. Carbons don't usually have lone pairs on them. And it has 3 covalent bonds. So the carbon has, 4 valence electrons, minus 3 bonds, minus 2 non-bonding electrons. That adds up to -1. So that lone pair on carbon means that carbon has a formal minus charge. Does that make sense? So it is that simple. Recognizing, and it should become automatic the more you see them, recognizing that the atoms that we have in the molecule don't have the right number of bonds or lone pairs that they should have if they're neutral, then we got to think about what might be the charge, plus or minus on it. Okay? So, are there any questions about formal charges? Yes?
So when drawing the structures during exam, should we specifically mention the charges?
Yes, if you draw a structure that has formal charges in it and you don't draw the charges, yes, that would be wrong.
And one other, there was an example in which one of them had the formal charge, negative, and so then again, in the next step, the next resonance structure, the extra lone pair was shifted to another carbon or something.
Right.
So the curved arrow, should it start from the negative sign or?
Yes, well, yes. Let's talk about curved arrows and resonance structures. We can do both at the same time. So hang on just a second. Let me clear this off. Okay, let me take, for example, one of the examples you might have seen something like, let's say I take something like this. Okay. Now, this molecule that I've drawn has a formal minus charge on the nitrogen. Oxygen has all the normal things, but nitrogen only has 2 bonds and 2 lone pairs. And if you calculate the formal charge like we just did, there's a formal negative charge on the nitrogen. Okay? Now, if I want to draw a resonance form, those electrons, and it doesn't matter which lone pair we're talking about on nitrogen, they're both the same, that lone pair on the nitrogen is adjacent to a pi bond or a double bond from the carbon to the oxygen. And so those are alternating, lone pair, double bond. And whenever you have that situation, or you have multiple double bonds, or even plus charges next to a double bond, that means the electrons can spread out. That's when we can draw the extremes of the resonance forms. So in this case, those electrons are delocalized between the nitrogen and the oxygen, and I can represent that by envisioning and drawing the electron flow from where the electrons start to where they end up, and that's how you draw the curved arrows. Okay, so I would start here and say that forms a bond now between carbon and nitrogen. Okay, and at the same time, the pi bond or the double bond on the oxygen, the electrons are pushed up onto the oxygen. Does that make sense? So if I draw that resonance form then, okay, we now have the double bond to the nitrogen, and we have a single bond to the oxygen, right? And now our negative formal charge is no longer on the nitrogen, because it took that lone pair that was the negative charge and made now a bond. So nitrogen has 3 bonds and 1 lone pair, which is what it should be neutral. Oxygen now has the wrong number of bonds to be neutral. This has the formal minus charge. Okay? So, and remember, neither of these structures exist. What exists is some combination of the resonance forms in between, right? Some hybrid. If you would take where the electron density is and sum it up, that's really a true picture, which is hard to represent specifically with lone pairs and bonds using Lewis or Kekulé structures, and that's why we have this concept of resonance forms. Notice the resonance arrow I used. A single line with 2-headed arrows, that's not an equilibrium. These are not, although we envision this and talk about these resonance forms as alternating back and forth, in reality, they're not. They're just describing extremes of what exists somewhere in between. Okay?
Hybrid resonance.
I would probably draw it. I could probably draw it sort of like that, with it's got sort of a half of a double bond between each, and overall there's a negative charge which is shared between the nitrogen and oxygen. And actually, since these both, if this was an acetate ion, okay, right, we did the same thing with acetate ion in class. If that was an oxygen here, then it would be essentially an equal part of negative charge on each oxygen. Okay? It'd be a half a negative charge on each oxygen, basically. If you did the quantum mechanic calculation and calculated where electron density was, it would come out to say there's a half a negative charge on each oxygen. Now, let me ask you then, would you expect it to be equally divided between oxygen and nitrogen in this case? You're shaking your head. Okay, anybody else want to guess?
The charge?
The charge, if that negative charge, if it's oxygen and nitrogen, would it be equally distributed on oxygen and nitrogen?
Yes.
The answer is no, and that's, if you think about the concepts of, we talked about electronegativity, the more electronegative atom would prefer to have more of the negative charge. In this case now, oxygen and nitrogen are no longer the same electronegative atoms. So I would actually, and I don't know, you'd have to actually do the mathematics and calculate the density based on the properties of atoms and their quantum, the nature of them. But there should be a little bit more negative charge on oxygen than nitrogen. Yeah.
I'm just kind of curious, could you explain, draw a curved arrow so that it can go from this side to that side again?
Yes. So if I want to go back, if I want to draw the resonance form in the other direction, I would just simply draw the arrows in the opposite direction. So we need to take a lone pair from oxygen, form a double bond to the carbon, and that will push the double bond here up onto the nitrogen. Okay, so that would go back the other way.
That is why kind of carbon-carbon there can never be a double bond between carbon-carbon.
Right. Yes, because remember, the carbon here is sp3 hybridized. Okay, and there's no way for electrons to flow through Resonance electrons are always going through pi system, a pi bond. So if it's just single bonds, there's no way you can have resonance. Good question. Any other questions about this example? Would you like to see more resonance form examples? I mean, you can draw all kinds of extreme resonance forms. For example, let's just take this molecule. Now, I have no negative charges, but there are ways in which we could draw resonance forms, because what we have are more than one pi bond which are adjacent to each other or alternating. So notice here we have a pi bond, a sigma bond, and then another pi bond next to that. So the electrons can actually flow between those. I mean, the electrons are really spread out over all of them. Let me just erase that. So I could actually draw, for example, if I take the electrons in this pi bond and shift it between that carbon-carbon bond, and I can now because there's a p orbital on both, and then push those electrons up onto the oxygen. Okay, let me draw the two that are there already. Then I can have a structure which looks like this. Okay, but I've left some things behind. Now I've taken away electrons from that carbon. There's a plus charge there. And I've added electrons to the oxygen. There's a minus charge there. That's a valid resonance form for that structure. Okay? And then to think about that going back the other way, you could just do the opposite. Electrons going to fill that plus charge. Okay? Now, we generally wouldn't write this because we know that what exists is actually closer to the more stable ones. These would be very different in energy if you just think about a neutral molecule versus one where we've actually separated charges. The energy of the separated charged molecule is going to be much higher. So probably along this continuum of structures, if you think about a continuum of electron density structures that you could think about, it's going to lie more closer to this. Okay? But what it's really telling us, though, is that looking at these two resonance forms, that when we have a molecule that looks like a double bond next to a CO double bond, and this is the more electronegative atom, that's why I push the electrons that way, that this is going to have some partially positive charge, and this is going to have some partially negative charge when we talk about reactivity. Okay? So that's why it's useful to understand what resonance forms are and how electrons are delocalized. So I think if I think about the orbitals involved, I'm just going to draw that. Okay? If I think about the orbitals involved between a C, 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 O, there's a double bond or a pi bond on the oxygen, and there's a pi bond on that carbon-carbon bond. Okay? And so what you can see is that there is a p orbital on that carbon, a p orbital on that carbon, a p orbital on that carbon, and a p orbital on that carbon. That's the key to resonance. If you understand now hybridization in orbitals and how pi bonds are formed, if this can overlap, the pi bond, if that can overlap, well, it can just overlap across the whole thing. That's why the electron density is spread out. And then the particular position of more electron density depends on the more electronegative atom. Okay? Hopefully, see, when we first covered this in Chapter 1, we hadn't really talked about how double bonds are formed in the hybridization. So it was difficult to really think about that in concept of those overlapping or adjacent p orbitals. So that's true whenever you have delocalization of electrons and charges, it's going to be through p orbitals that are all in a row. Okay, any other questions about resonance? No?
Are you going to ask us multiple resonance forms of the same structure?
I don't know, I may. I'll say possibly, or not. Okay, so I think we've covered, chapter 1 really is a lot of basic general chem. So you had a question?
Yeah, I was just wondering about on your practice test from '07 that you had posted when we were drawing resonance structures.
Mm-hmm.
The correct answers didn't have formal charges on it. So
the correct answer is on my key.
yeah, do you still? That's why I'm just wondering if you want formal charges on it.
Well, let's see. I have it right here. Let me take a look. I have the exam. Okay. See where it was. We can go through some of these problems too in a few minutes. This is the '07 exam.
Yeah.
Was it? Which problem was it?
Go
Up. Oh.
keep going.
Oh.
Right. Yep. Up one more. Right there.
Okay.
Forward.
Hopefully I didn't write it incorrectly on the key. But let's go through these, actually, since we're talking about resonance.
Maybe I think it's true.
Okay, if we take that first example, right, what I have is a CO double bond next to a carbon which has a negative charge on it. There's a lone pair on that carbon. By the way, we refer to that as a carbanion for your future information. So if I want to think about drawing the resonance form for this, notice that the lone pair is adjacent to a double bond. Okay, so we can delocalize that lone pair just exactly the same as if this was the example like that, right? It's exactly the same thing. It's just now instead of oxygen, we have a carbon with a lone pair. We can delocalize the same thing. So you can imagine those electrons flowing down to form a double bond and then breaking the CO bond. So the resonance form for that should be this. And hopefully that's what I drew in the key.
If you have to put the plus charge?
Oh, no. Carbon starts negative, and if it makes those electrons into a bond, then it becomes neutral. If it starts neutral, like in nitrogen or oxygen, which is neutral and donates, then it has more bonds, and the formal charge will be plus. Okay, like in this case on the right. This is a molecule which we call furan. Notice there are double bonds, 2 double bonds in this molecule, and lone pairs which are next to it. So those lone pairs, or at least one of them, can be in the same alignment as the p orbitals of these double bonds. So you could draw resonance forms for this. So for example, if I take this lone pair and make a double bond between the oxygen carbon and push those electrons up onto that carbon. Okay, what would that resonance form look like? Let me just be clear and show those. Okay. But that has more and less bonds to oxygen and to carbon than what we need, right? So there must be formal charges. And if you calculate those formal charges, this one is going to have a plus charge on oxygen and a minus charge on carbon. Intuitively, I hope you see that without having to calculate the formal charge, because what we've done is we've given away the electrons from the oxygen and we've given those electrons to the carbon. And so obviously oxygen becomes positive, carbon negative. Question?
In the first one that you did,
Oops, sorry.
would you want us to put in all the lone pairs in it?
You wouldn't have to. Like this makes perfect sense to me because I knew that in order to have one bond and a negative charge, there has to be 3. But it certainly doesn't help, especially if you are still trying to make sure you are accounting for everything, it certainly can help to write everything in and keep track of where they all are. By the way, I could take this and draw another resonance form. If I just take this negative charge and form a double bond here and kick these up there onto that carbon. There's a third resonance structure which is available to this molecule. And now that lone pair is here. Okay? So you actually have a lone pair from the oxygen in furan delocalized or spread out around the ring. Okay? In this case here, we have a plus charge. That's an empty p orbital. Okay, a plus charge is an empty p orbital. I'm sorry, a plus charge on a carbon. Let me just say that better. When you have a plus charge on an atom that doesn't have its octet filled, then that empty orbital is a p orbital. And that p orbital is adjacent to the p orbital on the carbons of this ring. Okay? In my poor crude drawings, oh my gosh. So that empty orbital also wants to be filled with electrons, and so you can draw a resonance form for this also. Undo all that. But in this case, this plus charge is empty, so we have to push electrons towards it. And we can form a bond. We can simply take the electrons in a double bond and shift them to form a double bond to satisfy that plus charge. So a resonance form that we would get when we do that would look like this. And that would leave the carbon we took electrons away from empty, so there's plus charge there. Not negative charge now, plus charge. This book, unlike the book that I originally took this from, doesn't really talk about plus charge delocalization in Chapter 1. It comes later. In the other book that we used to use, it would talk about both of these together. So I point this out because it was on this test, but I won't have any plus charge delocalization or empty orbital delocalization on this exam. But that's how that works. I know some people were wondering about that.
Yeah, because you just have one arrow.
Right, because there's nothing to push off. So when I use two arrows, I'm moving a lone pair down, but then I have to push off more electrons or break a bond. In this case, since the plus charge is already an empty orbital, I don't have to push anything away. It doesn't have an octet, so I can just fill that with the electrons by forming the bond. Okay? And this last one, you can draw resonance forms. So for example, I can take this negative charge down here and push that negative charge up onto that carbon. That structure would look like, I'm going to draw it here because I'm going to draw another one in a second. That would look like that. Okay. That lone pair can go, a better resonance form for this, I can take that lone pair and push it down here and kick those up on oxygen. A better structure for this is this. And actually, of those three resonance forms, this one's the most stable because the negative charge is on the more electronegative atom. And by the way, this is just the deprotonated form of phenol. And phenol is pretty acidic because it forms a stable anion which can delocalize all the way around the ring. Okay. Which brings us to another question. Acid and base. Right? What is an acid?
Proton donor.
Yes. A proton donor is a specific kind of acid, which we call a...
Artemius and Lewis Bronsted.
Yeah, Bronsted or Arrhenius acid. Bronsted really is the best way. A proton donor and a base is a proton acceptor according to Bronsted definition, a Bronsted-Lowry definition. Let me go back to a white background here. So, a proton donor is an acid, and a proton acceptor is a base. Okay? I know the Bronsted definition, but what about the Lewis definition? What's the Lewis acid then base definition? Yeah, a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Okay, slightly different, and the difference is because although H plus is certainly an electron pair acceptor, right? H plus will protonate or go to a lone pair and form a covalent bond to it. Other things can do that also, namely metals which have a plus charge or an empty orbital that can accept a lone pair and form a bond. Okay? So we have a broader definition of acid to include other atoms besides hydrogen as a lone pair acceptor. And that's really all the Lewis definition means. One thing you'll notice on the periodic table over there, right? You have boron, aluminum, gallium, indium, thallium, that column. That column of the periodic table has 3 valence electrons. Okay, so generally to be neutral, it has 3 bonds and an empty orbital. That empty orbital is available to form or accept a lone pair. So oftentimes, any of the elements in that column in the periodic table, and the halides, or even all kinds of compounds of them, if they have 3 bonds, they can act as a Lewis acid, okay, and form bonds. We gave the example in class of something like boron trifluoride. It's a neutral molecule, but has an empty orbital. And so there's no octet. It only has 6 electrons around it right now. So it's seeking electron density. Even if it becomes a formal plus charge or negative charge, it's seeking electron density. So if I take something like, well, let's just take water. Water with its lone pairs can donate its electrons. So this is the Lewis base. And this is a Lewis acid. And it can form a bond. I'm getting pretty good at these color codes. So then we would have something like this. So notice the terrible lone pair. This bond between the oxygen and the boron, the electrons came from the oxygen. The lone pair of the oxygen to form a covalent bond and share them with the empty orbital on boron. This now means oxygen has more bonds. It's given up electrons. And if you calculate the formal charge, it's plus. And if you calculate the formal charge on boron, it's gained electrons. 4 bonds to boron. If it only starts with 3 valence electrons, then it must have a minus charge. Okay? And overall, by the way, BF3 is neutral, water is neutral. If you combine them together, overall, while there may be formal charges, they have to overall, for the whole complex, be neutral, right? They have to cancel.
How is BF, I'm always confused with that one. BF3 neutral since it doesn't have an
Because it only starts with 3 electrons, it only has 3 protons in the nucleus. So it all depends on the atom's properties. 3 protons, 3 electrons. Okay, so with only 3 valence electrons, it cancels out all the proton charge, even though it doesn't have the 4th orbital filled with anything. Okay? Any other questions on Lewis acid-base definition? Okay, let's talk a little bit about acid-base equilibrium. So who remembers what kinds of properties lead to acid strength? What makes something a stronger or weaker acid? What properties of the molecule? Polarity, electron density, electronegativity, and overall, if you think about this equilibrium, HA, a proton attached to something that will give up the proton, plus a base, and oftentimes they're negatively charged or have a lone pair, so I'll just be neutral here and say base with a minus charge, is in equilibrium. Notice 2 arrows, not just one. Is in equilibrium if you transfer that proton from the acid to the base, you generate a new anion plus a neutral HB complex. Okay. So remember our definitions. This is the acid, HA. This is the base. What had given up the proton and becomes negatively charged or sometimes neutralized. On the right side of the equation is the conjugate base. And what gained the proton is the conjugate acid. Okay? So, you know that the equilibrium or this reaction will lie on the side of which of these is the stronger? I'm sorry, the weaker, right? So which acid is weaker? That's the side the equilibrium lies more towards. And the greater the difference, the more it will lie towards that side. Okay? So equilibrium lies on the side of the weaker acid. Or another way to think about it, and it's directly related, is to think about not the acid components, but think about the base components on either side. The base on one side versus the conjugate base on the other. It will lie on the side of the more stable base. Well, what that means, weaker acid means less reactive acid, and more stable base means less reactive base. In principle, it lies on the side of the reaction which is less energy. Okay? Higher energy is always more stable and more reactive. Less energy, more stable, less reactive. So you could actually consider the acid or the base, and when you're thinking about the relative strengths on either side or the relative positions. Okay? So, let's see. Was there an example on that exam? 2007 exam? Let's take a look. There must have been. Okay, here's a good example. Structural features which lead to acid strength. Let me make this bigger. Okay. Here's some examples, and they want to know which is the stronger, did I say acid or weaker acid? Stronger acid. I could ask which one's weaker, by the way. It's just the opposite. So. Okay, which of these of the pairs are the stronger acid? So the more electronegative groups, the more you can think about stabilizing a negative charge once it's formed, the more easily it'll give up that proton, or the more reactive or stronger that acid will be. So that's why the conjugate base, stability and the acid strength are directly related. So if we look at this example, the first one, we have a carboxylic acid with just carbons and hydrogens, and we have this is an acidic hydrogen. This is also a carboxylic acid, acidic hydrogen. Okay. Which one will more easily give up that proton? Well, the one that will more easily stabilize. So what we have here are 3 fluorines on the carbon, which are more electronegative than carbon. Okay? So that will be the stronger acid. And it's the stronger acid because if it gives up the proton and you generate the minus charge, okay, all these fluorines which are withdrawing electron density from that carbon are also pulling electron density away. In essence, it's helping to spread out the negative charge throughout the molecule, through the sigma bonds, or alleviating some of the influence of the negative charge. So that lowers the energy and makes it more stable. This molecule has no electron withdrawing groups, or less of them, if you will. So it doesn't have any effect on that negative charge as much as the fluorines will. Okay? So electronegativity. Let's see. Problem B. Who knows the answer to problem B? Is it the alcohol on the left or the alcohol on the right? Yes. This is the more stable anion because if it gives up that proton, it'll form an anion which is much more stable than if this one on the left gives up the proton. Why? One of the more important aspects of stabilizing charge is being able to spread it out. And this one can spread it out through resonance. We just had that example of resonance forms, right? So if it generates this negative charge, that negative charge now can be pushed into the ring, and actually you can draw 3 or 4 resonance structures for this. That negative charge could push down here and push this one up, and then that can push down here and push that one up. So there are several resonance forms you can draw spreading the negative charge out among 4 atoms. That's a more stable thing. So going from here to there by reaction with a base to take that proton off is going to be a heck of a lot easier, or the acid is stronger, than trying to take a base and take this proton off, where you generate a minus charge which is localized on a single atom. Okay, so that's an effective resonance. So question B here is all about resonance forms and stabilizing the negative charge. Yes?
In here, during exam, should we write down the lone pair for the oxygen and then show the curved arrow coming out of it and do the negative charge too?
For this question, all I needed you to do was circle the one which is the strongest one.
No,
Yeah.
for resonance structure.
Oh.
Question, the curved arrow
Yeah, so if draw the curved arrow,
from the negative charge.
well, it depends on how I ask the question. If I just say draw the resonance form, you could just draw the result of it. If I ask you to show how it gets there, which I may do, you never know, then I would draw it like this. Yeah.
That doesn't mean that carbon has 4 electrons. It's just the charge.
No.
Because in that one, the negative.
I see. So, yeah. I think part of the confusion is I'm trying to highlight that there is a lone pair. When we write these, usually, it's assumed if I draw a negative charge there, that there's a lone pair. That's right. So actually the correct way would probably be something like that. I'm just trying to highlight that it's there for you. It's not 2 lone pairs that I'm trying to represent. Okay? Yeah, don't get confused with that. I can see how that could get confusing. Okay, how about this on the bottom? Let's do D first. Water versus H2SO4. H2SO4, it's sulfuric acid. It's a really strong acid, and you should probably just know that. But why is H2SO4 a stronger acid than water?
dichroic acid?
No. Let's just think about just taking the first proton off. Why would that be easier to take off than water? Can you draw the Lewis structure for H2SO4? It's not an organic molecule, but it's just chemistry. It's just atoms. And if you know valency of atoms and bonding, and recognize that since sulfur is one row lower on the periodic table, that it could have higher oxidation states because of d orbitals. So the sulfate, or the sulfuric acid, we can draw like that. Okay? That's sulfate.
That's 5 bonds.
Yes. Sorry, sulfur has 6 bonds here.
6.
Yep. Because it can reach that higher oxidation state. Because it has those d orbitals. It has all those d electrons it can give up. So that's one of the things. When you start to go below the row we're most concerned about in organic chemistry, then you can do things like this, which wouldn't never make sense for oxygen, right? But think about if you take that off, this is also a resonance and electronegativity effect. Sulfur is more electronegative. But also, if that negative charge comes down and pushes up there, or you could push to the other oxygen, that negative charge is spread out through resonance. Sulfuric acid is very strong because of that. Okay? On this exam, tomorrow I'm going to focus on organic molecules, so know about your organic groups. This question was about understanding that you know basic valency and how many electrons are on things, right? Which one's the stronger acid? In the Lewis sense now, not just in Bronsted-Lowry sense. Yeah, obviously. This one has an empty orbital. This one, which wasn't written, has a lone pair. It has an octet. Obviously, this is not going to be a Lewis acid at all. It would be, if anything, it'd be a Lewis base. And for your information, trying to take a proton off of nitrogen is very, very difficult. Extremely difficult. Much harder than oxygen. Okay. Let's see. So, was there any equilibrium questions or anything on here? There may be some later. Okay. All right, any other questions about concepts in Chapter 1?
The sp3 hybridization.
Yeah, we're going to get to that. We talked about that a lot in chapter, where? Chapter 2? Yes. So let's talk about Chapter 2. Let's, let me get a white background again. Okay, Chapter 2, concepts. What do we have that are important? Okay, we talked about a lot about bonding and hybridization. Okay, we talked about, in that regard, don't worry about molecular orbital theory, but we usually describe organic structures using valence bond theory, thinking about how the bonds are overlapping from the atomic orbitals, because it's a little bit easier to visualize. You know what shape of a p orbital looks like, or an s orbital, or a hybrid orbital. Hybridization, sigma bonds and pi bonds, right? sp2, sp2, sp3. Chapter 2, we also talked about how to name molecules, so nomenclature. It's important to be able to speak the language. The IUPAC rules. And we talked a little bit about alkane reactions and reactivity, combustion. What else? How we describe oxidation and reduction in organic chemistry. Oh yeah, and polarity and dipoles. Right? Electronegative atoms create polarized bonds. Okay, so let's just review some of the bonding and hybridization. Hybridization is a concept, I think, which people struggle a lot with because it's abstract, and what we're really talking about are mathematical computations of probabilities of finding electrons. Orbitals really aren't real. They're not like solid things. They're just regions of space where we would expect a higher probability of finding the electrons that are located there. So it's a probability map. But we can think about that shape and the alignment and the orientations and how they overlap with the orbitals on other atoms to get an idea about how structures are put together and their shapes and their orientation in 3 dimensions. So when we have organic molecules like things that are made of carbon with 4 valence electrons, right? And we have to form 4 bonds by sharing, overlapping with other things. Could be another carbon, could be an oxygen, could be a hydrogen, or many other elements. We have to figure out how that's bonding, okay? And based on, if you just had atomic carbon, you would have an electron configuration, if they were s and p orbitals, of a filled s shell in the valence shell, and 2 of the p orbitals having 1 electron each and 1 p orbital empty. And there's no way you could form 4 bonds if it's configured like this. Okay? So that the calculations we have that describes the mathematical, the shape of those regions in space, right? For an s orbital, it's a sphere. It's spherical in shape. And a p orbital is dumbbell shape, and I always draw it like this, but actually it probably looks more like this. It's just harder to draw. A p orbital, this is also important to recognize, that's 1 orbital. So an electron or a pair of electrons in that orbital could exist anywhere in there. Keep in mind that there's a region of space between the nodes, between the lobes, around that atom where it could exist either on top of it or on the bottom of it, but not in between, which is another concept which is very abstract. It can be here or here and can move from one place to another, but it can't exist in between. So p orbitals have directionality. So if you have 3 p orbitals, there's 1 in the x direction, and there's 1 in the y direction, and there's 1, okay, that's 1 orbital, that's another orbital, and then a 3rd orbital in the z direction, right? So if you had 3 p orbitals, it would look like that. So if you imagine a carbon with an s orbital in the middle, you know, your s orbital's in the middle, and you have 3 p's that are oriented in 90 degrees apart, that does not describe the bonding of organic molecules in the shape, right? It adopts a less energetic conformation where we have the electrons as far apart as possible in those bonds. And that is what geometric structure for a carbon? A tetrahedral. Right? So a carbon has a tetrahedral shape. And in order to have that shape, we can't be using the orientations and shapes of orbitals that are S's and P's. We have to come up with 4 equal orbitals. And so mathematically, if the S and the 3 P's are all combined and then parceled out into 4 equal energy orbitals and equal shapes that could orient in a tetrahedron orientation, that is what we refer to as the hybridization, made up of 1 S and 3 P's combined and then split out to 4. That's an sp3 hybridization. Okay, so what we now have are 4 equal orbitals which have shape properties that are very similar to a combination of an S and P's, right? It still has a little bit, we don't often draw it because a lobe on the other end is not that big, but a sp orbital actually probably looks something like that. This little lobe on the other end is a remnant of the p orbital, but it's not where most of the electron density could reside, the probability, and so it's the other end of the lobe where bonding takes place. Okay, so there are 4 equal orbitals, even though I'm not drawing them equally here. 4 equal orbitals, each with an electron in it. And so if you take those 4 orbitals and put them around a carbon, oh, I'm running out of space here. Let me erase this. Okay, take those 4 orbitals and put them around a carbon, right? You have a carbon atom. You could have an orbital in this direction. That little lobe I'm not going to worry about, so I'm not going to draw it. Then there's an orbital in this direction, and then there's an orbital coming out towards you, and then an orbital going back. That's the tetrahedron. Okay? Now we can form 4 bonds. So methane. So if you think about 1 electron each from carbon, now we can take 4 hydrogens, say an overlap with an s orbital of a hydrogen, and make methane. Okay, and that describes the shape. Notice if you have sp3 hybridization, 1 s and 3 p's, add that up, that's 4, right? 4 bonds to carbon, we can only have single bonds, or sigma bonds. So an end-to-end overlap is a sigma bond, whether it's between an sp3 orbital and an s of a hydrogen, or an sp3 orbital of 1 carbon and an sp3 orbital of another carbon. If they end-to-end overlap, that's a single or a sigma bond. Okay? Is anyone struggling with the concept of this hybridization to make sp3 hybridized carbon? And other atoms as well. Nitrogen is sp3 hybridized. Lone pairs will end up in a hybrid orbital because it's electron space. Whether it's a bond or a lone pair, electrons repel, and so they want to be as far apart as possible, and to do that they hybridize. Okay, now to make, you had a question? Someone had a question? Okay.
So
Sorry, I just erased that.
hybrid orbitals are lower in energy than normal orbitals?
Hybrid orbitals are lower in energy. So if you really plot out the energy from an S and P's, because we don't have just atoms existing in atomic state like this, they're bonded in molecules, right? So they're actually somewhere in between. Overall, they're between the S and the P. But it's the lowest energy state once you form a molecule. Okay, once you actually have to form bonds, it's lower energy to do that for equal orbitals than, again, if you have 3 p orbitals and an s in the middle, there's no way you can even overlap and fulfill an octet, right? And so, yeah, that would be very high energy to try to bond like that. Okay, so a thing to remember, sp3 hybridization is tetrahedral in geometry. Okay, it's 4 equal bonds. Actually, I should probably hurry up because we're going to run out of time. 4 equal bonds, or lone pairs and bonds. And it can only be single bonds. There can't be multiple bonds in an sp3 hybridized atom.
Can't be what?
You can't have multiple. You can't have double bonds or triple bonds, because these are all 4 orbitals pointing as far apart as possible, and so there can't be side-to-side overlap, only end-to-end overlap. If you need to make a second bond, right? If you need to make this, there's no way you can do that if it's sp3 hybridized. And so the shape of something like this is what we would call trigonal planar. That is, there are three equal spacings in one plane. So if you look at either of those atoms, it looks like that. It's flat in one plane, trigonal planar, 3 equal bonds, and then 1 pi bond. So we have a sigma bond, and here we have a sigma bond, and here we have 1 sigma bond and 1 pi bond. Okay. In order to get the second bond between the atoms, one of the orbitals on each carbon has to be left as a p. Okay, so let me clean this up and show you sp2 hybridization. So again, if you think about the orbitals that we start with for carbon, instead of mixing all 3 p's with the s and coming out with 4 equal orbitals, we want to combine only 3 of the orbitals. We're going to combine 1 s and 2 p's, and then leave 1 left alone. Okay, so our new electron configuration is going to look like 3 sp3, and the shape is very much similar to the that should be sp2, 3 sp2 orbitals, because it's made up of 1 s and 2 p's. And then there's 1 p left over. Okay, so that's the electron configuration that describes now bonding when you have to make a multiple bond. In the orientation then of those orbitals, you'll have an s orbital, a sp2 orbital there. You'll have an sp2 orbital here. You'll have an sp2 orbital there. Okay. And then the p orbital is here. Okay. So we have 3 hybrid orbitals spread out in 3 things to find a plane, and then we have a p orbital perpendicular to that. That's what allows a side-to-side overlap with another p orbital. So, if I don't run out of room here, think about another carbon with an sp orbital, sp2 orbital, an sp2 orbital there, an sp2 orbital there. Ooh, I'm really running out of room. And a p orbital. This now is overlapping side to side. That's not 3 bonds, remember. This is 1 orbital above and below, but they overlap on both sides. So that's 1 bond, a sigma between them, and then there's 1 pi bond between the carbons. That describes double bonding in anything. It doesn't have to be between carbons. This could be a carbon and a nitrogen. This could be a carbon and an oxygen. Those would still also have to be sp2 hybridized to have a p orbital. Okay? So sp2 orbitals are trigonal planar, or the flat, the 3 bonds are flat, 3 sigma bonds, and 1 pi bond, or 1 empty orbital. I point that out because remember, the neutral configuration of boron molecules, let's just take this for example, has the same shape. If it has that same shape, you should assume it's sp2 hybridized. And it's sp2 hybridized because one of the orbitals is empty and doesn't take up any space in terms of electron repulsion. Empty p orbital. So this and this and this, those sigma bonds, have to be made up of, since there are only 3 of them, 1 s and 2 p's, or sp2. Does that make sense? Hopefully that helps clarify it for people who are having difficulty with that. So if you have an sp hybridized, what does it look like? 1s, 1p, that means you're only combining 2 orbitals to make, then you have to split it up into 2 equal orbitals. And the shape defined by 2 equal orbitals would be linear. They'll just be as far apart as possible. Right. So an sp will be linear. It's made up of 2 sigma bonds and 2 pi bonds, or empty orbitals. I guess I should make sure I reiterate that. A p could be an empty p. And so I'm not going to draw that, you don't know 1s and 3 p's. I'll just say there are 2 hybrid orbitals, sp, which again looks similar, and then there are 2 p orbitals, which are dumbbell shaped. So that describes what the contribution from a carbon that's sp hybridized. The 2 p orbitals have to be 90 degrees apart, orthogonal. So if I want to draw a picture of, say, I should start at the top of the screen here. If I want to draw a picture of, say, acetylene. Ooh, I don't want that. Okay, acetylene. That's a triple bond. Triple bonds are sp hybridized. There are a sigma bond, and there's a sigma bond between the carbon, and then there are 2 pi bonds between the carbon and a sigma bond there. So you see the bonding? Now to draw that pictorially, like I did with the alkene, carbon with an sp hybrid orbital and an sp hybrid orbital, linear. That's not a p, those are 2 hybrid orbitals. So there's the hydrogen. Overlapping with another carbon with another sp hybrid orbital. Okay. Then we have the p orbitals. So in orthogonal or 90 degree apart directions. So just like the double bond, we'll have an overlap of p orbitals side to side in one axis, and then we'll have an overlap of p orbitals that's coming out towards us and going back away. So let's see, this is closer to us, so I'll just shade this in. Okay, this is on top and underneath. And in the back, that's overlapping in the back. So does that, hopefully, my crude drawings give you some sense as to what the shape of that is. So the blue bond is a sigma bond. There's one from one carbon, one orbital from another carbon of hybrid overlapping. Then there's a pi bond, which is red, made of p orbitals. And there's a pi bond that's in green, made of p orbitals. Okay, linear, sp hybridized. Carbon monoxide, if you look at the Lewis structure for carbon monoxide, CO, that's the Lewis structure for carbon monoxide, which has a formal minus charge here and a formal plus charge here. the carbon and the oxygen are both sp hybridized, because to make 3 bonds between them, we have to have 2 p's left on each atom unhybridized. Okay? Any questions on hybridization and the shapes? Yep.
So if it's sp3 hybridized, normally it's 105 to 109.5 degrees.
Right, tetrahedral, close to 109 degrees. Yep.
And if it's sp2, it's 120, and sp 180.
Exactly. Yep, you got it. Let's see. Hybridization, bonding, sigma bonds, pi bonds. And so some of those examples on the old exams, if you've seen it, looking at a molecule, can you tell how many sigma bonds there are and how many pi bonds and how many lone pairs, things like that? Okay, let's talk a little bit about naming. How comfortable are you with the naming rules and nomenclature? Anybody have problems? Speak up. Okay, you have some examples you'd like me to do?
The ISO stuff.
ISO, okay. If you always answer, if I ask for a name and you use IUPAC rules and don't worry about the common name, you'll always get it right. Okay, so I'll say that up front. But you will see me use a lot of common names as well. And if you use a common name, it certainly wouldn't be wrong as long as you use them correctly. So in general, there would be, so methyl substituent, right? Propyl, a propyl substituent would be attached to 3 carbons. I use that squiggle to indicate that's a bond to something else. Okay, something else is here. This is a 3-carbon group. So that's a propyl substituent. We often use isopropyl. That's an attachment on the middle carbon, so something else is here. And there's a joke in there somewhere about an isopropyl people eater or something. Yeah.
So iso means kind of in the middle.
Iso means it's an isomer of, and so commonly that's for a small chain like 3 carbons, there's only 2 ways to attach: propyl normal or propyl as an isomer. What's the official IUPAC way to name that isopropyl? Here are 2-methylpropyl. This is good. We're doing this because complex substituents, remember, you no longer look at the whole chain. You start from the point of attachment and find the longest chain from there. Okay? So you have to start number 1 at the point of attachment. And so from that position, what's the longest chain? Doesn't matter either way you go, it's the same. So I'll just say 2, right? So this is not a propyl group. This is an ethyl. And there happens to be a CH3 or a methyl group on that ethyl in the 1 position. So this is a 1-methyl ethyl. Okay, so be careful with those complex names. That's important to get that right. That's the most common mistake I see people make, is forgetting that it looks like propyl and it becomes automatic. We think 3 carbons propyl, it's an isopropyl, but no. If it's a complex substituent naming under IUPAC rules, start at the point of attachment numbering 1 and then find the longest chain from that. Okay? Other common ones, I'll just point out. You might hear things like tertiary butyl. That's an isomer of butane where the attachment is on a tertiary carbon. That is a carbon attached to 3 other carbon groups. So tertiary butyl, that's a a tertiary butyl group, or tert butyl, we abbreviate it as. Other than that, I don't know that I would use a whole lot of other common names for these small substituents. There are other common names, but less commonly used. Let's take a look at some of the naming things on the test. If I can find it. Okay, here, draw some structures. It's a lot easier, I find, when people are trying to do these types of problems, to go from the name to drawing the structure, because the name is pretty self-explanatory. So let's take a look at this. Now we have a situation where we have a ring compound. In this case, it's a cyclobutane is the parent name. Okay, cyclobutane. Don't forget that cyclo part. That's the parent. So this is cyclobutane. Okay. This book used other substitutions. I'll use just carbon groups in this test. But 3-fluoro, 1-ethyl, cyclobutane. There are groups on 1 and 3. So you can pick any position to start with a ring. Let's just say we'll put an ethyl group here. And 1, 2, 3 away would be a fluorine substituent. But remember what happens with ring molecules. Because it's a ring and there's not always free rotation, one side of the ring is different than the other side of the ring. So we have to say whether these groups are up or down relative to each other. So this is prefixed with trans, and that means opposite side, right? So one of these groups is coming up, one of them is down. It doesn't matter which one you put up or down. It's the same molecule as long as the relative positions are that way. So to indicate something's coming up, make sure you draw it right. You need to make a bold wedged bond. So if I take this fluorine, for example, and draw the bond like that, that means it's coming up out of the board. And if I draw the bond to the ethyl group with dashes, that means it's going down away from you. So those are on opposite sides of the ring, the trans molecule. Okay? Number one thing I see also people making a mistake is in either naming something or drawing a structure is missing that, missing cyclo. So don't forget about that. Okay? How about this one? 6-ethyl 2,3,4-trimethyl octane. 1, 2, 3, 4, 5, 6, 7, 8. Start with a parent chain. That's 8. Make sure you double count. That's the second most common mistake in drawing molecules. They forget the ends, or they miscount the number of ends and corners in their molecule when they draw line structures. Let's see. There's 3 methyls, 1 on 2, 1 on 3, and 1 on 4. And then an ethyl on 6. Okay. You could also write that out, by the way. You could write it out in this form. Oops, 2. You know, put 8 carbons in a row. Please don't use condensed formula. This is about as condensed as I'd like to see it. I'd like to see those bonds between the carbons. Otherwise, it's harder to see that skeleton and whether you put it together right. Oops, so that would be CH3, CH3, and so on. So you could hopefully do that, right? Okay, this next one is a complex substituent. Again, using the systematic naming, notice it's in parentheses. We put complex substituents in parentheses. And outside of the parentheses is where it's attached on the parent chain. So here we have, oh, come on. Here we have decane, 10 carbons, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons, and on the fourth carbon, 1, 2, 3, 4, we have a 1,2-dimethyl propyl. What does that look like? Well, complex substituent, the parent chain of the complex substituent is the propyl. So you can start just writing 1, 2, 3. Okay, that's the propyl. Let's be clear now. Here's the point of attachment. That's the side chain. This is the number 1 carbon. Okay. So what's branched off of that propyl? There's a methyl group on the 1 carbon and a methyl group on the 2 carbon. So that's the complex substituent. Now, if you saw that complex substituent, could you name it if I gave you the structure? Okay. What else do we have? Let's see. I'm going to have to break out of this, move this up. Bromo. Okay, here's another one. Here's a cis isomer of cycloheptane. Cycloheptane. It's a ring molecule, right? And how many carbons? Methane, ethane, propane, butane, pentane, hexane,
7.
heptane. So start 1, 2, 3, 4, 5, 6, 7, and it does, oops, that's 6. I need one more carbon. Oh! 1, 2, 3, 4, 5, 6, 7. And be careful, that doesn't look like a bond. That doesn't look like a carbon because it's not pointed enough. It takes a little practice to write those rings that are bigger. 6 is easy, 5 is easy, but 7. Okay, 1,4-dichloro. So cis, I could write them both up. 1, 2, 3, 4. Again, I could start anywhere since it's a ring, but then the other second substituent is relative to that. So I can write them both up like that, or I could write them both down, 1, 2, 3, 4, like that.
Is there anything related to axial and equatorial?
Okay, axial and equatorial. So I'm going to get to that. Not 7-membered rings, we haven't really talked about conformations. 6-membered rings we have. Are there any more questions on nomenclature, naming? Because I think we do need to talk about cyclohexane conformations a bit and alkane conformations. So use the rest of the time I think we have to talk a little bit about that. Actually, I have one example here in this test. Okay, I'll come back to this in a minute. We know that molecules are in motion, and when you have a single bond or a sigma bond, you can freely rotate one atom relative to the other, and it's constantly happening. But once you start putting other groups on there are energetic consequences to that. If bonds become closer together, electron repulsion energies become higher, that strain, torsional strain, or large groups come close together and they start bumping into each other. So we need to understand and have an idea about how molecules move and how they rotate and what those conformations look like when we freeze it in space. So we can represent organic molecules like as a sawhorse figure. So if you look at ethane, these are supposed to be tetrahedrals I'm drawing. Looks kind of like a sawhorse. I've drawn it in one specific conformation. If I rotate one relative to the other, I could draw a sawhorse conformation which looks like this. Okay? And it's a little more useful to visualize this than the orientations if you're looking down one bond between carbons and seeing the front relative to the back. That's where we use the Newman projection, right? So would you be able to take, say, those structures I drew and visualize and draw a Newman projection from it? So if we're looking down this way, there's our eyeball, and we're looking down that carbon-carbon bond. On the carbon closest to us from that view, what do you see? Projected flat onto the paper, you would see a bond straight up, and a bond to the left, and a bond to the right. Oh, my drawing's terrible. Okay. You see that, the carbon close to you? Now, in the carbon that's further away from you, which way are the bonds pointing? The other three bonds of the carbon, which way are they pointing? I'm talking about this bond here. It's pointing straight down, right? From your perspective, that bond in back is pointing straight down. Okay, and then there's a bond up to the right and a bond up to the left. So that's the Newman projection showing the relationship between the carbon close to you and the carbon further away. Okay, so notice the relationship between the software structure and this. The frozen in time conformation I've drawn on the bottom, what does that look like? I'll draw it a little smaller so I have some room. Again, looking down this way, we have a hydrogen going down straight, and a hydrogen going up to our left, and a hydrogen going up to our right. And in the back, right behind it, we have a hydrogen going straight down, and a hydrogen going up to the left, and a hydrogen going up to the right. So it's a different conformation, right? Staggered and eclipsed. Staggered and eclipsed. And which one is higher in energy? Eclipsed, that's right. Because of the bonds overlapping with each other and there's more electron repulsion.
Considered,
Huh?
that's Derek strain?
No, that's torsional strain. That's electron repulsion is torsional strain. So electrons in this bond are repelling the electrons in that back bond. Simply, they're closer together, so that electron repulsion is higher than in the top case. 60 degrees apart, 0 degrees apart. Okay? So let's play around with these two. If I take this and put a CH3 group there, okay, and then I rotate that around, does it change the energy of any of the conformations if I put it there, or if I put it in this position, or if I put it in this position? Nothing changes, right? Each of those staggered conformations will be identical in energy. Let's see, if I have that here, okay, this will be higher energy than the top one, but again, each of those, if I were to put it here or here, each of those conformations would be each of those energies would be the same, right? So with ethane or propane, this is propane, right? Now we have one carbon in front, a second carbon in back, and then a third carbon coming off of it. That's propane. We talked a little bit about butane. I'm just going to draw this again, two conformations next to each other. We talk about butane. I'm just going to draw the staggered and the eclipsed. Okay. So with ethane, all those positions are hydrogen. Let's say we take butane, which is 4 carbons in a row. And again, I'm looking down the middle two. So there's a CH3 on the front carbon and a CH3 on the back carbon. That's 4 carbons in a row butane, right? So they're in that staggered conformation, they're pretty close to each other, right? If I rotate now around it, let's say instead of having it in this position, we put it down here. So 2 staggered conformations that we can compare. One of them is higher in energy than the other. Okay, because there's groups closer to each other. That's a gauche interaction. This 180 degrees apart would be what we refer to as the anti-conformation. Okay, same thing with the eclipsed. We have the CH3 groups next to each other. They're going to bump into each other. That is actually going to be different now than if this was just a hydrogen in the back and I put the CH3 down here. Both eclipse conformations, because they both have higher torsion strength, but of those two, this one will be lower energy. Okay? Anybody having difficulty seeing that and understanding that concept?
My issue is with torsional versus steric strength.
Yeah, so that's adding both, right? Relative to that.
So if you look at the gauche formation,
Yep.
or the gauche conformation, that CH3 and that CH3 would be having both a steric interaction and a torsional.
Yeah, but torsion is minimized to some extent here because it's 60 degrees apart. This would be, if it's on the top case here, those two, that would be the highest energy of all the possible conformations.
So it would be the highest.
Yeah, so remember, in butane we looked at the fact that if it's the anti here, anti, that's the lowest energy, and then we rose in energy to a gauche conformation and then to another staggered, this is eclipsed, this is staggered gauche, and then up to this position, which is this highest energy position, down to staggered, eclipsed, and so on. So notice, even though this gauche interaction is higher in energy than the anti, there's the gauche. It's still less energy than the eclipsed. Did you follow all my scribbles? So that's acyclic. That's molecules which are not rings. Remember when we fix things in rings, it's more rigid. And size of ring matters to being able to adopt different conformations. But most importantly, we talked about cyclohexane. Okay, so just briefly, we can see that of just how the ring can move, the lowest energy conformation will be in the chair conformation. Okay? So we can write that, again, by drawing parallel lines. 2 parallel lines, that's the middle bonds. And we can do it this way and then this way. Okay? And remember, the lower lines are closer to us as we're looking sideways at the ring. And the lines on the top are further away from us. Although I'm not drawing bold and dashed here, that's the perspective you need to visualize in your mind. Okay? I could do it the other way. Okay? And those are a little close together to draw everything I wanted to, but so be it. So that ring can flip to this one. Yeah.
How do you get from that structure to this structure?
Let me show you. What happens, let me just map these atoms out. So this red atom here is this one here. So this swings down to that position. Okay. This one swings up, and this one swings up, and that goes to these positions. Are you following that?
I'm talking about from the actual that structure, the first.
How do I get from here to here?
No, the other one.
From here to here. Well, this is just flat. That's just I've drawn a cyclohexane flat on a paper without indicating any 3 dimensions. This is the 3-dimensional picture. Okay? So I'm going to erase this and draw a big chair so that we can take a closer look at it. Okay, chair. So we draw a chair structure, and at every corner of that ring, if it's pointing towards the up, there's an axial bond pointing straight up, and if it's pointing towards down, there's an axial bond pointing straight down. So I'm going to draw those in red. So there's an axial bond, there's an axial bond, there's an axial bond. No more is pointing up. Okay. Here's an axial bond pointing down, here's an axial bond pointing down, and there's an axial bond pointing down. Okay. We have 3 on top alternating every other carbon, and 3 on bottom alternating every other carbon. The equatorial bonds, a little bit harder to draw. I usually, for ease, just start on the end and draw the equatorial bond, which I'm doing in green here. Notice it's parallel with the 2 middle bonds. Okay. On the other end, we also have an equatorial bond going up, slightly up in a way, which is also parallel with those 2 middle bonds. The other equatorial bonds are parallel with bonds right across it, so that one's parallel with that one. Okay. And the one in back, slightly angled a little more because it's parallel with this bond that's closer to us, the carbon-carbon bond. You see that? So there's equatorial bonds there, and there's equatorial bonds there. Okay, it's hard to draw chairs without lots of practice. You noticed if you looked at that 2007 exam, I got tired of trying to figure out everyone's chair, so I just gave it to you. and drew it for you. Said put something on there. But it's useful to practice that and get used to doing that, because then you get a better sense as to the shape and structure. Okay, we look at this chair. We have axial and equatorial. Question?
Like when that chair flips,
Yep.
is it a conformer?
Yes.
Okay.
When that chair flips, it's a different conformation. If you have groups on the ring, they will switch. So as this flips down, that red bond that's axial will swing down and become equatorial, and the green bond, which is equatorial, swings down and becomes axial. Every position is doing that, because as that swings down, this one's swinging up, so this becomes up and then out, and then down and up. Okay? So if you start to substitute this ring, oops, I don't want to do that. If you start to substitute this ring with different groups, then we have different energetics. If it's all hydrogen, one chair is the same energy as the other flipped chair. If you have groups on there now, one is not the same. So if you have a methyl group, I could put one methyl group on the cyclohexane, and if I put it there axial, okay, or I flip the chair and it becomes equatorial, one of those is lower in energy. Why? Yeah, it's steric strain because of the other axial positions. Okay, those come close to each other. So it's bumping in or coming closer to 2 other groups, whereas if it were in the equatorial position, it'd be further out in space and without bumping into anything. So bottom line, axial positions are more crowded, higher steric strain, higher energy than equatorial positions. And so if you were to look at the two conformations, you should know which one is higher energy, which one is lower energy. Okay? Now, let me just get rid of some of this stuff here. Oh, can't I undo this? Okay. Now, if you think about this, again, alternating around the ring, and keep in mind, this is the 3-dimensional picture we often draw this flat. We just draw it as a hexagon flat, right? And we indicate groups like if there's a CH3 group up. Let's say there's another CH3 group up. Okay? On the adjacent carbon, sorry, it's writing off the screen here. If it has two groups, which are cis, depending on where they are located, 1, 2, 1, 3, or 1, 4, they're going to have influences on that conformation in different ways because this is up position, this is down. Okay? Get rid of this. The next position over, the one on the top of the ring, is going to be equatorial, and down will be axial. If you go to the next carbon over, the up position is axial, and the down position is equatorial. So you see how I'm doing that? And so that alternates all the way around the ring. So if it's cis, or on the same side, and it's on 1, 2, one's going to be up axial, one's going to be up equatorial. Okay? If it's 1 and 3, one's going to be up axial, the other would be up axial. Okay? Then if you flip it, they're both equatorial. One of those is going to be a lower energy. I didn't say if it's 1 and 2 here, 1 and 2, one is axial, one is equatorial. If we flip it, you're still going to have one axial, one equatorial. So if you really remember, every axial becomes equatorial and every equatorial becomes axial. You might not even need to, you can even just remember, well, how many are axial and how many are equatorial. Then if you flip it, it's going to, those numbers would just alternate or change. I think I was rambling there. Did that make sense? Okay. Anything more about these that you're confused about, these chair conformations? Or you have questions about?
Even larger molecular weight atoms that you have.
Oh, yes, good point. So this difference between the strain energy of being axial versus equatorial, of course, is a steric interaction. So the larger the group is, the more it's not going to want to be axial. Okay? So if I have something like a methyl group here, and then let's say on the 3 carbon I have equatorial, I put a large group like an isopropyl. Okay? This is going to be equatorial with plenty of space. This is going to be axial, okay, which is more crowded. If I flip this ring, what happens to those two groups? If I flip it, this large group, this isopropyl, or 1-methyl-ethyl, will become axial, and this one will become equatorial. So now I have a much larger group axial. That's worse. Okay? That's higher energy. Oops. There's so this problem. And here I used ISO. If you were trying to name it, you wouldn't have to use ISO. But let's take a look at this. The lowest energy conformation of 1 isopropyl, 3 methyl cyclohexane, and they're on opposite sides of the face of the ring. They're trans. Okay? So remember, think about up, down, up, down. I made this problem way too easy, I think, because I drew the chair and I even draw boxes where you put your group in, so you know. So let's think about this. So if this is carbon 1 and this is carbon 3, let's put the groups in. So we could put, we have to put a methyl group, CH3 group over here, and in an isopropyl group, or a 1-methyl-ethyl over here somewhere. So up position, down position, where are they going to go? The other empty position is going to be a hydrogen. So We want the isopropyl group in the lowest energy conformation to be equatorial. So that's equatorial. That means this one has to be hydrogen. Okay? If now these groups are on opposite sides of the ring, it's the trans molecule. This is the down position. This is the up position. This is up. This is down. So CH3 has to be up. If the isopropyl is down, CH3 has to be up. So I have to put it here. Okay, that means this has to be the hydrogen. So that's the correct structure then for that lowest energy conformation. And if you can get that, you could think about the highest energy conformation of the cis molecule. Okay, and it's very simple. Cis means they're both on the same side. 1, 3. I can put my isopropyl group in the axial position, up. That's an isopropyl, really. And hydrogen here. And if it's on the same side of the ring, I have to have the methyl group up and hydrogen here. That's the highest energy conformation because they're both axial. Or otherwise they'd both be equatorial. They'd both be in the down positions. Okay? Questions?
When naming some compounds, when you have like a cycloalkane, a substituent.
Yes.
Is the C on the cycle considered part of that?
Of the name?
Yeah, like
For alphabetical reasons?
Yeah, for alphabetical reasons.
Oh, now you're nitpicking the fine points that I never remember. So even I messed that up. I think so, because it's part of those a part of that group, as opposed to a di or a prefix to it, di or tri or
So
etc.
it's not considered really a prefix.
No, it should be part of the name, so I think it will be. But if it comes down to that, I'm not going to worry about that for alphabetical order. As a matter of fact, I don't care much about alphabetical order too much because you get the same structure regardless. And you're just alphabetical order. Try to do it, but if it comes down to something like, do you remember if it's the cyclo is counted or not? I'll give it to you. So. Okay, I think you're getting tired, right? All right. 1 o'clock tomorrow. If you have questions and you want to email me or anything, I'll try to answer my email, and I should hopefully be around tomorrow morning if you have questions and want to stop in.